Okay, so just a little bit left in 1.6 to cover here. We have one more theorem, and then kind of an application of some of this stuff. So this theorem, this final theorem, is going to be the converse of a theorem that we proved before, and I had mentioned when we covered that theorem that the converse was true, but we just weren't able to prove it yet. So now we're ready to do that. The theorem I'm referencing is the one that says that if A and B are invertible matrices of the same size, then their product, A times B, is also guaranteed to be invertible. In fact, its inverse would be B inverse A inverse. So we proved that back in 1.4. Now we want to go the other direction. Suppose we don't know if A and B are invertible, but we just know that they're square matrices of the same size. If we happen to know that their product is invertible, so if AB is invertible, this theorem is stating that A and B must also be invertible. Now there's a couple of ways of proving this. A faster way of proving it is using determinants, but we need a bunch of development in that area that we cover in chapter 2. So rather than wait until then to prove this theorem, we're going to use what we know from our equivalence theorem now to do this. So let's suppose A and B are square matrices and they are of the same size, and that AB is invertible. Those are the assumptions that are being made in this theorem. We want to prove that both A and B are invertible. So let's suppose, first of all, that x naught is any solution to this linear system. This is going to start to feel like a proof that we did in the previous video. If x naught is any solution to this, then I'm going to plug x naught into a different linear system. What happens if I do AB times x naught? Well, AB times x naught, I can regroup this by putting my parentheses here, would be A times bx naught. Bx naught, though, if x naught is a solution to this system, is equal to the 0 vector, the 0 matrix, and A times 0 is the 0 vector, or 0 matrix. Now remember, we assumed that B is invertible, and that means if we look at the linear system ABx equals 0, our equivalence theorem says that that should have exactly one solution, the trivial solution. So that would imply that x naught has to be the trivial solution. It has to be 0. Okay? So what does that tell us? Well, x naught we had originally chosen as a solution to this system, and we didn't know whether or not B was invertible, so we weren't able to apply our equivalence theorem here yet. But if we just chose this arbitrary solution of this this system, and then we went and showed that that actually means that x naught is the 0 vector, then that means this original homogeneous linear system bx equals 0 also only has the trivial solution. By our equivalence theorem, that means B is invertible. Okay, so now we need to also show that A is invertible. So if we have this, AB times B inverse, and we kind of shift the parentheses using our associative property to this, A equals B, B inverse, this would equal I equals A. What did we just do? Why did we bother doing that? Well, remember, from the assumptions made in the problem, AB is an invertible matrix, and we just showed that B is an invertible matrix as well, so B inverse must also be invertible. And this product of invertible matrices gave us A. We already had a theorem, and we just talked about it, that says if you have a product of two invertible matrices, then that product must also be invertible. Therefore, A is also invertible, and that finishes this theorem. Okay? All right, last thing we want to do is look at linear systems of this form, AX equals B, where A is not necessarily invertible. If A is invertible, this is essentially too easy, because according to our our equivalence theorem, if A is invertible, then this has a unique solution, and it can be found by just doing A inverse times B. So we've dealt with that now. But what if A is not invertible? What can we say? Well, if A is not invertible, then this linear system is going to be either It's either going to have no solutions at all or infinitely many solutions. And it turns out the case of whether it's got infinitely many solutions or no solutions at all is going to depend on what this vector b looks like. So if we have a singular matrix, meaning not invertible, A, then the system AX equals B is going to be consistent for some vectors B, but inconsistent for others. So how do we determine which cases for B give us consistent systems? Well, we use Gaussian elimination for that, and I'm going to illustrate with this example. So let's say that we have this linear system, but notice the constants are arbitrary, B1, B2, and B3. I don't know what those constants are. I'm keeping things general. So what I want to do is determine for what values of B1, B2, and B3 will this system have solutions? Will it be consistent? So I'm going to start by creating an augmented matrix for this. 2, 1, 0, negative 1, 0, 2, 3, 2, 2, and then I have B1, B2, B3. Okay? So let's work on our Gaussian elimination here. So even though I don't have a 0 here, I'm going to go ahead and swap or interchange rows 1 and 2. Row 1, interchange with row 2. And the reason for that will become apparent once I do this. That'll be a B2 now. 2, 0, or sorry, 2, 1, 0, B1, 3, 2, 2, B3. Okay. Remember, if I'm going for Gauss-Jordan elimination, I want 1s on my main diagonal, and by interchanging the rows, I now have a 1 in this entry where it should be, and I also have a 0 here and a 0 here. I'm ultimately going to want zeros there. So it seems like interchanging those two rows did a lot for me there. Next thing I want to do is make this a positive 1. So I'm just going to multiply row 1 by negative row 1. So negative R1 is going to replace R1, giving me 1, 0, negative 2, negative B2. Nothing else has changed yet. 2, 1, 0, B1, 3, 2, 2, B2. Okay? Next thing, I'm going to do 2 steps in 1. I'm going to try and get the zeros below the 1 in this column here. So I can multiply negative 2 times R1 and replace R2, or add that to R2. Let me change that. Negative 2 R1 plus R2, replace R2. And then I'm also going to do negative 3 R1 plus R3 and replace R3. Sorry, that's a little bit messy there. Okay, so my first row is not changing. 1, 0, negative 2, negative B2. Multiplying by negative 2 and adding to my second row, I'll get 0, 1, 4. Let's see, negative 2 is going to become 2B2 plus B1. 2B2 plus B1. So you notice now the constants are starting to look like expressions, linear expressions in those unknowns, B1, B2, and B3. Multiplying my top row by negative 3 and adding down, I'm going to get 0, 2, let's see, that becomes 8, and then negative 3, it's going to become 3B2 plus B3. Okay? Now I'm going to do one more step of Gaussian elimination, and something interesting is going to happen. I have zeros below this leading 1. I have a leading 1 here. The next step would be to produce a 0 here. So I'm going to multiply row 2 by negative 2 and add that to row 3. Negative 2, row 2 plus row 3 will replace row 3. Okay, so I have 1, 0, negative 2, negative B2, 0, 1, 4, 2B2 plus B1. Now, if I multiply by negative 2 and add down, I'm going to get 0, 0 again, and 0 again. What's going to happen here? Well, I have to multiply this entire expression by -2 and then add it to this. So that's going to give me -4b2 plus this 3b2 should give me -b2. And then multiply by -2, -2 times b1 plus this. There's no other b1 terms to combine with, so that becomes -2b1. And then this b3 here had nothing to combine with either, so that becomes b3. Okay? Notice the row of zeros. We should have expected that from the very beginning. And why? Well, I had said that we're going to be working with a singular matrix, right? A is not invertible. Even though it's not stated here, I sort of hinted that this example would include a singular matrix. And what happens when you row reduce in a singular matrix? You get a row of zeros. We know that because according to our equivalence theorem, if we did Gauss-Jordan on an invertible matrix, I should have gotten the identity matrix. But I have no hope of that now. So this is a singular matrix. And remember our goal, we want to determine conditions on these three unknowns here, b1, b2, and b3, that would give us a consistent linear system. Well, when you get a row of zeros, there's two possibilities. This will either imply that our system has no solution at all, or it has infinitely many. And how do we distinguish between the two? Well, the determination is made based on whether or not this is a contradiction. This will be a contradiction if this is equal to anything other than 0. But if we want to have solutions to this system, then this last row should be 0 equals 0. In other words, this expression here should be equal to 0. What happens if I do that? So if I set -b2 minus 2b1 plus b3 equal to 0, and then if I solve this for b3 equals 2b1 plus b2. What this does is it tells me what b3 needs to look like in terms of whatever b1 and b2 are. So what this means is that in order for this system to be consistent, then the vector b, representing this column right here, has to be of this form. b1 and b2 can be whatever they want to be. We think of that as like parameters in a parametrized solution set. But b3 has to relate to these two this way, 2b1 plus b2. Okay, and that is what we were looking for. If you wanted to verify this, what you could do is pick any numbers that you wanted to for b1 and b2, and then use those values to determine the corresponding value for b3, and then put those in to this linear system up here. Solve that linear system with Gauss-Jordan elimination, and you should see an infinite number of solutions in your result. If you want to see it not work, pick values for b1 and b2 here, and then put something down here for b3 that would not occur from plugging this b1 and this b2 in. What you should see in your Gauss-Jordan elimination is a contradiction once you get to this step, implying that there are no solutions at all. Okay, so yeah, that was it for section 1.6. We have one section left to cover in chapter 1, and we'll be done.